Hello and welcome to this webinar presented by DEWESoft USA. We always mention this at the beginning of all of our webinars. If there is a subject matter that is of interest to you, please do not hesitate to let us know. We can certainly tailor existing webinars, and of course we are always interested to know what subject matter is of interest to our users. That said, let's get started. As with many subjects for which we have a passion, we like to begin with a little bit of background. This helps to understand just what we are dealing with, as well as making some aspects of it easier to appreciate. Then we will look at the structure of CAN, keeping in mind that understanding the actual composition of a protocol will often help make sense of certain aspects that may appear less than obvious. We will try not to get into too much detail, and some images may appear for a very brief period. This is because we don't want to totally lose the plot. We will then take a moment to quickly review the different formats of CAN. CAN itself, CAN FD, XCP, CCP and so on. Although some of this will be relevant when we get to the last part, which is actually interfacing with the various formats, how they function and how to make them work, including a look at how the additional features available in X3 can help you even when you do not have a database, for example. We always like to get things in perspective before getting into the real nitty-gritty, and in the case of CAN, that is achieved by simply showing an image representing the Empire State Building and stating that a lot of people refer to CAN as vehicle networks. Well, the Empire State Building has a CAN fire detection system, and we personally wouldn't refer to the Empire State Building as a vehicle. The actual system uses CAN Open, which is a de facto standard for many sensors that offer CAN. Now again, we won't dwell too much on the pre-CAN history, but worth noting is that most communication protocols exist because of folks like Alexander Graham Bell. He of course is extremely well known and recognised as the father of the modern telephone. But one person is worthy of note that was a major in the US Army, George O. Squire, who coined the phrase multiplexing due to the fact that he basically invented it. And of course, it is that fundamental technology that provides us with the ability to deal with many of the primary communication protocols that we use today. The signals illustrated represent what early multiplexing and clock-based state changes may have amounted to. The example illustrated introduces a number of useful aspects of communication protocols: the state, binary, hexadecimal and time period relationships, and we'll cover these later. If it were simply binary, it could be the 010011 and so on, seen below the signal. However, if the groups of binary represented a hex value, it could be 4ECA, or decimal 4, 12 and 10. Sorry, 4, 14, 12 and 10. Or these could be the entire hex equivalents of 4ECA, which is 20,170 in decimal, or to introduce a complexity that we will review later, the endianness, which could imply a value of 51,790 or 20,170. A significant difference, I'm sure you will agree. Now, jumping ahead because we don't have the time for an extensive history lesson, the first introduction of CAN was at the SAE World Congress in 1984 in Detroit. It was announced by Robert Bosch, and they have to this day remained the helmsman of the CAN ship. It's worth noting that CAN as a standard utilises the 9-pin D connector, the same as was used in the RS-232 serial communications. A coincidence? Possibly. There are actually only 2 pins and a reference needed in CAN, whereas RS-232 uses all 9, if you count the ground, which actually leads to a very important aspect regarding CAN. That is that pins are shared, whereas in RS-232 there were RX and TX dedicated connections. Perhaps that is another reason that CAN was preferred over RS-232. Which leads us to this slide. Some people believe the reason CAN became so prevalent and popular was because it could ultimately reduce the amount of copper that was being used in many vehicles. Now the y-axis represents yards or meters of copper. I suspect that while there may be a very small grain of truth to this, it should be considered a modern day myth, although some large vehicle manufacturers are actually using the frame as the conductor in a single wire CAN. This animation is to emphasize the fact that CAN is a controller-based network, hence controller area network. That implies that the devices are as active as they are passive. They can provide almost real-time dynamic augmentation of some systems. After all, for the older of us, remember when you could rotate a distributor to adjust the timing? These can perform that same process 1,000 times in less than the time it took us to wonder where we left that special wrench to loosen the distributor clamp. There are a slew of acronyms out there, and CAN is a minefield for anyone new to the arena. So I've added a few key ones that you may encounter or hear from time to time. Don't worry, there will be a lot of these before the webinar is over. UART, which as you can see is Universal Asynchronous Receive and Transmit, is a good one because it does to some degree bring the whole thing into perspective. It is the basis for almost all serial communication systems, as well as having an important clue in its name, asynchronous, as in not synchronous. A couple others here are the buzz ones, such as XWire, which is basically autonomous vehicle-based protocols with redundancy, or a collection of others such as GM-LAN, FlexRay and so on, and one that isn't really an acronym, Ethernet. This is really important now because many of the younger guys know it so well they are basically replacing mostly the others with it. Ironically, XCP is a variant of CAN that sits on Ethernet. Oh, I should mention all CAN or even USB. This is really just to illustrate the evolution of some of the protocols. Keep in mind that ones like VPW and PWM were really the forerunners of today's CAN anyway. They just didn't have the broad take-up that CAN had and were dedicated to specific manufacturers. These were almost fated to fall by the wayside as they would have been supported by dedicated groups within each manufacturer. The worst possible thing was that they really didn't want to share. Now this is really just a review of some of the historical implementations of networks, as it also includes VPW and PWM, and it also suggests individual names as users of specific protocols. But the reality is that there are almost likely a mass of users of each of the more modern variants. Each protocol has its own characteristics. One of them is of course the speed, the rate at which the information is being passed around the network. Ironically, some of the earlier ones, such as SignBus, were significantly faster than those of today. The problem is that speed isn't always related to the bandwidth. Going fast is only useful if you can get a whole lot of information on it. The implementations of CAN-FD are designed to accommodate those needs. FlexRay kind of does, but it is more or less a backbone that combines different buses as opposed to a full-out protocol. Some of these have become all but invisible as they have been encapsulated into other systems, often via a backbone, which is another name for a universal hub. To a large degree, many of these have either disappeared or have been incorporated into more conventional descriptive and naming conventions. Now, as we previously mentioned, some devices are placed on the backbone. FlexRay utilises a backbone, but really it is the backbone. It is intended to somewhat simplify the combinations of various communications present and in use today. The clue is in the image. There is a hardware component. This indicates that it is not just a protocol. There is more to it. There are a lot of variants of CAN as well as ISO standard protocols. These are to some degree inclusive to one another, and so if you see ISO 11898, chances are you are also seeing SAE 2411 or a variant therein. Some of the variants are really intended to simplify things such as sensor interfacing. CAN Open describes the procedure for setting, addressing and initializing the communications in a way that just doesn't apply to SAE J1939, for example. The electrical type, as you will see later, the physical layer, is important if you need to know how many wires you're going to need to and from devices and controllers. Some networks will take advantage of the ability to have both two-wire and single-wire devices. So there is a need to at least have an appreciation for this as we get into the interfaces. High-speed CAN such as CAN-FD is covered in SAE 2962-2. The list of transceivers is growing rapidly. There are way too many controllers used in CAN today. Oh, sorry, connectors used in CAN today. There are too many controllers as well. This is really to show some common types of connectors. The nice thing is that these are pretty standard connectors, so readily available. Unfortunately, the pin assignments don't follow. For example, pin 7 for CAN high on a D sub becomes pin 6 on a J1962 OBD2 connector, C on a 9-pin Deutsch and A on a 3-pin Deutsch. Luckily, there are usually only two critical connections, so it should be relatively straightforward. The potential stumbling block is that there may need to be termination in this interpretation. Now let's have a look at the structure of CAN. It may not ever influence what you're planning to do on your device, but it is worth noting that CAN is event-driven, whereas FlexRay is time-driven. It may not matter, but in the event that you don't see what you expected to, it may be because the event that would have driven you seeing it simply may not have happened. There are specific timing requirements for CAN, as you'll see in a moment, but for the most part, messages will only happen if they were allowed to happen. The title of this slide is to introduce a concept using CAN that we will cover later on. That is how to deal with things that really are all happening at once. The Volkswagen Phaeton was one of the most advanced vehicles on the road. This image was a tremendous, in its day, this image was a tremendous way to bring home the nature of the intelligence incorporated into its design. As you can see, the model looks surprisingly similar to a human anatomical model. I'm pretty sure this was deliberate. We won't dwell on these next pages. These are really here to at least show some of the how the timing works on what is an event-driven network. These are really just to show some buzz acronyms that you may hear. For example, here T-segs and of course the phase segs. Believe me, this is really for the transceiver designer level. Again, quick flash for a moment just to get a couple of other keywords into the conversation. Synchronization and propagation. The fact is that there is nothing on the DAC side that should ever infer synchronization. This is literally only for the transceiver level. However, it introduces a key aspect of CAN, arbitration. This is critical for any system that has many devices trying to communicate at the same time. Again, a quick flash here, but there is one key phrase in this, and that is that the network is passive and only can become active at any one time. And this is why CAN is so fault tolerant. And we can explain that later in a more detailed webinar. Do you see the similarities of the DB9 serial communication connection pins? Now this illustrates the transceiver voltage characteristics. Although you may never have to concern yourself with this level of information, it is important in an event where you may need to troubleshoot an issue. Electrical signals are great telltales, of course more so when something is missing. This is really to illustrate a very important difference in single wire CAN to the more common dual wire. One other very important facet is that it introduces a series of multi-speed capabilities of CAN. On the subject of single wire CAN, as you can see here, the single wire CAN is actually the odd man in the bunch. Almost all other implementations are dual wire, and it to some degree makes a little bit of the resolving a little bit easier. The state of two wires can be compared with a single wire, only one has to be relied on. It doesn't mean that it isn't as reliable and that it is actually an important thing to keep in mind. There are basically two mechanisms for defining state. These are based on both period and initial state. They are respectively known as the NRZ non-return to zero and the Manchester methods. As you can see, the timing, and no, this isn't a contradiction to the earlier statement about CAN being an event-driven protocol, plays a large part in deciphering the equivalent value at any given point. And you might want to note that NRZ is the most commonly used format. Now this image has its uses. In this example, we're just trying to demonstrate a couple of important features of most networks. There are things that need to happen relatively quickly, and there are those that do not. As you can see from the animation, the brake lights are slower than those of the sensors reporting the status of the ABS sensor. We have highlighted a couple of things in this image because the concept of sharing information is very important. It's also a potential issue when we get information from a DAC perspective. It might be that it has been passed around to a number of controllers and devices before we even see it, and it may not be exactly the same value as it was when it originated from its device. Now this animation is to illustrate a very, very important feature of CAN. Only one device can speak at a time. Well, actually it really means that only one device can be listened to at a time. And if you note on this particular animation that the device 00 is doing a lot more than any of the other devices, and that's actually deliberate. It's because 00 in SAEJ 1939 doctrine is usually the EEC1, the ECU, and therefore it will probably have the most frequent and the most required pieces of information that it needs to share with other devices on controllers on the network. Now the purpose of this set of animations is to illustrate the basic functions of the application layer. at least to some degree, as other layers can instruct the application layer as to what it should do based on some event. Under normal circumstances, any and all devices on the network can communicate in one form or another. This may be just a heartbeat to say that it's still present. When you add a DAC, it also has to have an address. A common and to some degree reserved in SAJ 1939, for example, is FB. The DAC then becomes part of the network. Any node can request from any node or device that has been allowed to join the network. If a device on the network shows an error, it can be switched off, effectively booted off the network. Now keep that in mind, because if your DAC happens to be the device in error, the DAC could be kicked off the network. And now, emphasising one aspect of CAN that is extremely important to understand is that CAN is event-driven, not time-driven. Now sadly, we have to accept that there has to be an all-purpose model upon which CAN as a protocol as well as a system is built on. In this case, it is the OSI, the Open Standards for Interconnects. You know it as you probably use it on a regular basis. It is what the internet is built on. The good thing about it is that there is a wealth of documentation on it as well. If you really want to get into it, we recommend a quick review on the very place it lives, your browser. Now, unfortunately, much of the OSI is abstraction, so it needs a little lateral thinking to make sense of it. However, as a brief review, the preceding screens provide something of a broad overview of it. The physical layer. We'll take a moment on this slide. The rest will pass through very quickly with just the title as an explanation. The reason for that is because this is the layer that you will interact with the most. This is where you will physically connect to the bus, as well as add sensors, controllers, and so on. The data link layer is responsible for segmentation and frame manipulation. And keep the word frame in mind, it gets used a lot. The network layer is the equivalent of your home router's traffic management system. The transport layer is really the first aid station in the model. It checks that transmissions are healthy. The session layer, the point at which devices are checked on the network. This comes into play if you need an ACK and you forget to set it. This layer then refuses you entry onto the network in effect. As we mentioned before, when a DAC becomes part of the network, it must be allowed to stay on the network, and it may require that it has an ACK in order to remain there. The presentation layer. This makes sense of incoming information and basically ensures that the format is conducive with the system that you are trying to use it on. And then finally, the application layer. If there was such a thing as an app portion of the model, this would be it. This is where important things such as acknowledgements and decisions on priority are made. Now, the active, passive, aka dominant and recessive components are the critical factors in CAN activity that determines what communications are taking place at what point and which will ultimately be made available on the bus, or as it's often referred to, get control of the bus. Now, we've alluded to it but not elaborated on the outcome of the dominant and recessive parts, as well as how ultimately we get the information that is made available. Sadly, to get to this, we have to enter the rabbit hole and take a look at some key factors, such as hex and binary. Now, it's worth being aware that CAN has a system in place that allows for messages of greater importance to get control, as we mentioned before, of the bus. This is important because it implies that some messages may not get through when you expected them to. Again, something we mentioned before. Therefore, an absolutely important facet of CAN is its ability to deal with the level of importance attached to communications. This is achieved using prioritization and arbitration. Now, note that FlexRay has no arbitration as it's time driven. In this example, we see 4 competing sets of information trying to get heard, and only one can be. Now, in this you can see that one message is effectively one arbitration. It ultimately will make it through to the rest of the network, including you if you're attached. However, at this point, it is worth getting familiar with binary, as it demonstrates much clearer the mechanism that allowed the message to get through. Now, unfortunately, we need to appreciate the binary, the hex and the decimal. For a moment, just to appreciate that troubleshooting CAN may be a matter of checking bit values and locations, or at least hexadecimal values. This example is actually the SAJ 1939 parameter for engine data, the one that comes from the EEC1 we mentioned earlier. Now, the PGN, the parameter group number, is 61444, as defined by the so-called Blue Book. This is of course F004 in hex, and in binary it's one of the easiest because F is all ones, 0 is all zeros, and 4 is 100 or 0100. Now let's look at the formats involved and figure out how we get to a piece of data based on the information that was allowed on the bus. Now there used to be 1, then 2, and now there are basically 3 formats of CAN. They are CAN standard, CAN extended, and now CAN FD. However, the basic construction of a frame has remained to a large degree consistent. This shows the outline of a frame. It's almost the same for CAN FD. This illustrates the structure for CAN standard and CAN extended. There is a specific number of bits allocated to each component of the frame. These vary based on the CRC requirement as well. A bigger identifier typically implies there will need to be a bigger CRC to check it. And a CRC is the cyclic redundancy check, for those who are non-familiar with this. Now, as you can see, the payload with FD has been significantly increased, along, ironically, with the speed at which the frames can be made available. I guess newer technologies, faster, better, and all that. The FlexRay frame is decidedly more complex, but the payload is a huge factor bigger even than CAN FD. Now you'll notice, as mentioned before, that the data portion has grown, and so the CRCs, the cyclic redundancy checks, have increased dramatically as well. The cyclic redundancy checks are basically the checksums, if you will, to make sure that the message is, well, not corrupted, I guess. Now this is really to emphasize that XCP is actually a protocol that can reside on CAN, Ethernet, or even USB. Now because it is a protocol, it requires interpretation as opposed to dedicated hardware, unlike FlexRay. Now in this illustration I have missed a critical player in this, but only because this is more to illustrate development on a user level, and they are inclined to the hardware and primary communication protocols. Who actually remembers the old PC 104 development platform illustrated in the upper left? Now as you can probably see from this image, GMLAN is fundamentally CAN with all 3 speeds thrown in. This means that you can configure most of your incoming information in the same way as all CAN would be, with an addition of a protocol signal. This is something that may be multiplex and could spread across multiple frames. Just check the box for multiplexed in X3. Now this is very common across all manufacturers. By far the most common file format used in CAN applications is the vector DBC. This format is really a structured text file. It was probably originally created before XML was taken up on a large scale, so it didn't quite make that structure, but it is similar. The naming conventions are simple. BU, for example, is the frame identifier, BO is the frame wrapper, and so on. So the creation, editing, and other interactions with the DBC shouldn't cause too much confusion. As you can see, it is identify, explain, repeat. The use of CCP is a significant step beyond DBC level CAN. This is because a DBC fundamentally will describe what it is, where it is, possibly with a how to ask for it. But that is about as far as it goes. The CCP and XCP level is where you can get the same stuff as well as tell devices to prepare and send very specific pieces of information, as well as providing the ability to write entire memory blocks, thus affecting that information in the first place. Now, great care should be taken when using these beyond the interrogate level. Although there are probably many more, under normal use the chances are that you may access the network in one of 3 modes. These are CAL, which is the level that transmission developers, for example, may use, as it allows them an opportunity to tweak specific parameters one at a time. DAC, our typical place of interest, is where we can either periodically request a piece of information that is located in potentially a dedicated memory location on a controller, or it may be that we actually instructed the controller to make it available at that location. And finally, we may have defined a set of specific parameters to be made available from a specific location and followed on with a command that told it that that set of information should be broadcasted periodically, and then we merely listen out for it. And finally, the programmer's level, where entire controller memory maps can be deployed. This is really intended for the electronics development folks, and we should in the DAC world, avoid this particular activity as much as we possibly can. Remember that we can really mess things up if we aren't completely aware of what we put in where. Now these can all be encapsulated into a single DLL, or they may have individual DLLs. Always make sure that you have these DLLs available to you. Now the fact that XCP and CCP can provide access to a programming level on the network should not be taken lightly. Have you ever had an opportunity to update the BIOS on a computer? Do you remember the warnings that any loss of power or interruption during the process could render the computer unusable? I'd keep that in mind when using XCP and CCP at anything other than a DAC level. Now it's important to note that, as previously mentioned, XCP is capable of dynamically influencing a piece of information. It is also important to note that while some folks may intimate that it is real time, it isn't. With anything that involves serialized communications, there will always be a phase skew. The really nice thing about protocols such as XCP and CCP is that you can get a lot of information that simply would not be available on CAN, especially just the legislated CAN. That said, in DAC mode, you may well have access to data much sooner than it may have become broadcast, for example, as mentioned earlier when we were talking about the availability of messages. This also means that you could be seeing something that hasn't been manipulated by the scaling factors of those other devices and the other routing. No offsets and possible algorithms, so keep that in mind if the numbers are not quite what you expected to see. The A2L format, as with the ROG that are used in XCP and CCP, are fundamentally programs. That is to say that they are akin to the BIOS that you may write to your home PC. Therefore, since that is their intended purpose, they can get pretty large. The animation on the right illustrates just how large these files can be. We started by scrolling and quickly gave up and started using the scroll wheel. So down here, if I play this to show you, you'll see here we're just scrolling through, and you can get an idea of the length of this file by the amount of time that's remaining in this video. And I'm certainly not going to sit here for 5 minutes and 45 seconds to show you this entire file. It's huge. Now we can start looking at what we see and what we are interested in. When we go to the interface, we may need to construct the entire anticipated frame. This particular PGN is from the original SAE Blue Book. As you can see, there are some components that are defined and a couple that are potentially, and we say potentially because we probably should be prepared for possible changes, subject to some change. These are the priority and the source. Theoretically, the PGN otherwise would be constant. Oh, and by the way, this is just so we know what we're looking for in the proceeding payload. Now this is to illustrate a slightly different approach by a specific manufacturer, and this, by the way, is why there are things like the OBD2 standard in place that uses a PID or protocol identifier. In this example, you see the vehicle speed being defined as being in message ID 0200, keeping in mind that generally at this level parameters are described by hex almost always. Then it describes that it starts at bit 0, is 16 bits long, aka word, has a scale of 0.125, no offset, and it is signed. Although there is no guarantee, most 11-bit messages are Motorola based and most 29 bits are Intel based. That's basically big endian and little endian, and don't confuse endian with bit ended. Now we'd like to wrap this up by starting with a video of some data, then showing you how easy it can be to get to this from your CAN signal in as fewer clicks and as little effort as possible. So you see here a video playing which is just actually monitoring engine speed from an SAE J1939. And you can see the engine start and you can see it idling. And we've just set up a very simple display just to show that, and we're going to manipulate that in just a moment. So here we're adding a digital meter in, and this digital meter can actually show the hexadecimal values as they're coming through the bus. So we'll move on. So always start by making sure that you have your hardware configured correctly, and any extensions that you plan to use added and active. It's always a good idea to check that you're in an acknowledge mode for most automotive applications, and really important at this point, check that you have the required termination. Sorry, we only alluded to that earlier, but it is very important, and it's a 120 ohm resistor across CAN high and CAN low, and that's only if it's required. Here we are demonstrating the behavior of some hardware when analog and CAN data is collected at the same time. It also shows the ease with which a completely new CAN signal can be extracted if you know where it is and what the effectors are on the signal. We start by adding a strain gauge channel to the analog inputs. In this example, we start from scratch. It's a 350 ohm quarter bridge, and we can take advantage of the shunt to calibrate the channel quickly. And you'll probably notice that we are compensating for the lead wire resistances, we are balancing it, and we are making sure that the shunt equivalent represents the anticipated value that was displayed. So now we can actually see that our target was 2914, and it actually went to 2915. Now I'm just changing the limits on this one manually just so that I can see the data a little clearer. Then we have a quick glimpse of the CAN source. This is actually the same as an ECU on a truck. So we're going to take a quick look at the signal we're getting from the strain gauge first to make sure that that's working okay, and we can show you the combination of the two. So now we move over to the CAN. And when we move over to the CAN, the first thing we do with the CAN is we check to make sure that we're on the right CAN. This is a quick glimpse of the CAN signal generator that we're using, which is simulating an entire CAN stream coming from a truck. So it's going to replay a startup event as you saw in the previous video, and that way we know we're talking the right language. Then you'll notice that when we go to the CAN interface that we're getting a bunch of error messages. The reason why we're getting this bunch of error messages is because we're at the wrong speed. Most SAE J1939 implementations run at 250 kilobaud. And here I'm just changing it over so that I can view it as a hexadecimal value as opposed to the binary values, because I personally find the hexadecimal a little bit easier to reference. So now I've identified that I'm pretty sure that that F004 that we spoke about before, the EC1 message, is available. So what we do first is we basically make sure that we have selected that message because it's being broadcast, since we use the scan option. And then we know that engine speed is located at bit 24 and it's 16 bits long, and that the scale factor is 0.125. You can probably remember that from the previous screen showing the blue book. So we add those values in, and we can see an equivalent down in the lower right hand corner almost immediately. Now we can start reviewing the analog and CAN data visually, and all we're going to do here is add the CAN signal in at the same time as the analog signal, and that way we can see the analog signal and the CAN signal happening together. Now in this particular case, what we're going to do here is put that engine message so that we can see the entire message that we're filtering out, if you will. And we'll have a nice analog display to show the engine speed, and as you can see right now, when we switch to engine speed, we're in the idle mode. And if we sit here long enough, we can actually watch the engine rev up, and then we'll see the data coming from the strain gauge at the same time. So here we're just setting some limits so that we can actually see when the value exceeds a defined value. In this case, we're going to say any more than 1250 RPM is a warning limit. I'm going to minimize these so that it's a little bit clearer. And now we're going to do our strain gauge to show the strain gauge data. So there's our strain data, and here is our CAN data. And right now the engine is going to restart. So we'll see the engine restart, and we'll see the CAN data change as the engine restarts. So it's pretty straightforward to add a CAN signal, and in this case an analog signal, into the same test. Now we could have just simply loaded a database. So we load up a DBC file. When we load up the DBC file, we'll see that particular message, if it's available, very quickly. If it's included in the DBC, it will automatically translate that message into meaningful engineering units, if you will. Now the XCP, if you want to use XCP or LIN, it's a plugin. So these could be loaded in using the option dialog. Once they're added in, they become additional icons at the top of the screen. And then all you need to do is set the communication parameters such as IP address for XCP over Ethernet, and then load in your A2L file. So it's pretty straightforward to even do something similar to XCP or LIN and so on. Now CAN FD, the same sort of process. Again, set your act behavior. Once you've set your act behavior, make sure you're speaking at the same speed, and then load a database, pick your signals, and you would have almost instantly noticed the difference between the CAN standard, CAN extended, and the CAN FD, in so much as you now have 64 bytes of data that you can parse out. So it gets pretty big. And finally, if you want to simply see and record the OBD2 standard messages, add the OBD2 extension and select the respective OBD2 file, which may not be required, and then select what you want to use. And it's a matter of just telling it whether you want to use it or you want it to remain unused. A very powerful tool in the developer's arsenal is the ability to broadcast on CAN. This is particularly useful if you are testing the behavior of a sensor which you plan to add to a network. It is also a very useful tool if you want to make peripheral data available to devices on the network. In this example, we start by adding our sensor, as we did before. Again, the strain gauge will balance, we'll compensate for lead wire, we'll apply the shunt to make sure that it's correctly calibrated, and then we'll just set our full-scale limits to a slightly lower value than before. And once we've set our full-scale values, the channel is ready. Now for this example, we're going to add a video channel in as well so that you can see the actual event as it's happening. So I'll just quickly set up my camera, which I have placed over the strain gauge, which is on a small piece of brushed steel. And then we go into the CAN. So we're going to set our CAN message for TX, which is transmit. Just like all CAN messages, to have a wrapper or frame, and then the component parts. In this case, I'm going to simply add my strain gauge as is onto bit location 1 and make it 2 bytes long. So I start off by telling it I want to use FF01, set it to 10 milliseconds so that it repeats pretty frequently. Call it strain gauge out. Doesn't really make any difference what I call it. Doesn't really matter what units I put on there because I'm just going to be broadcasting this on CAN, and then I'm going to assign it to the strain gauge channel, and then immediately once I've set it to the correct sign, I can see in the lower right hand corner some values as I bend the strain gauge, so I can see the CAN signal is changing. So I'm now going to use the transmit option and look at the data, just set up my display here so you can see everything. And once I've set everything up so you can see it all, turn the camera off, which is a kind of pointless one in the stream. There's my strain gauge channel. I'll add in my video, and I'm going to place it at the top of the screen here so that there's a little bit of room to put in the device I'm going to use to actually monitor the CAN signals that are coming from the device. So there is my video so I can see it happen, and then I'm going to use, just testing it out quickly, and then I'm going to use a device called the Peak device to actually monitor for the CAN signals, and you'll see the CAN signals are changing here as I bend the strain gauge. It really is that simple. So CAN is fundamentally free data. It can extend way beyond data when you use protocols such as XCP and CCP and so on, but at the end of the day it can provide a wealth of supporting information that is already there. In a matter of minutes, a 64 channel test with loads, strains, temperatures and so on can be enhanced with peripheral and supporting information from CAN. This could overshadow the analog data by significant amounts, but the nice thing about it is all you had to do was add a couple of wires and you were done. And the keyword is free. So once you have your DS CAN or you're serious with CAN, you are ready to go. We'd like to thank you for participating in this presentation, and don't forget to keep an eye open for future webinars. We'll now open it up for any questions and answers. You can type your questions into the chat. Note that we will read out and answer as many as possible in the time available. If you want to ask a question offline or we run out of time, please contact us using the information displayed. I will be joined by John Miller and Matt Enquist and Mike Davis, along with our support team in Ohio. So thank you once again. We are now open for Q&A.